Okay. So all of you can hear me. Good. That's good. Great. So, hello, good morning, students. Vishal here. And as usual, we are going to continue yesterday's class. We'll wind up. There is a small topic left in yesterday's class. We'll complete it and we'll start a new chapter today. Okay. Cool. So, please, have a technical check. I'm audible, right? I'm audible to everyone. So, having a small check here. So, if I'm audible to everyone, please let me know. If there is any issue, also please let me know. Okay. So, good morning, everyone. Okay. Great. So here we are. So let me tell you what we are going to do today. So today's class will be a continuation of yesterday's radiation topic. Yesterday we just skipped a little bit, right? We saw what is heat transfer, what is Newton's law of cooling, and we just skipped a little bit of radiation. So we'll be going to radiation today, and we'll start thermodynamics. In the second half of the class, we'll start thermodynamics. Okay, is that clear? And it's very simple, right? Yeah. Okay, so by the time, so again you can respond if I'm audible. That's a quick technical check. Okay. Yes. Okay, guys. Then if everything is cool, we are good to go. Okay. So let me tell you very quickly. As I told you, what are the topics which we are going to study here in a bit detailed way. Okay. So the first 30 minutes, imagine the first 30 minutes we'll be talking about radiation. In radiation, we'll see what is an actual radiation, what are the different kinds of radiation, okay, and how do they transfer heat, okay, how do they transfer heat, and if you heat a metal, it's going to change color, okay, initially it will be red, then it changes color to white at the most highest temperature. Why does this happen? And how can we explain? How can we understand this particular concept? We'll go through it. Okay, and that is also given by a law called Wein's displacement law. Wein's displacement law. Okay, so we'll go through Wein's displacement law as well as Stephen's law. They're very simple. They're just like 2-3 variables at all in the whole equations. So once we are done with black body, radiation, heat, and Stephen's law, we are good to go with thermodynamics. In thermodynamics, I'll just briefly tell you what is PV and NT, pressure, volume, number of moles, and temperature. And detailedly we'll discuss about work done, heat, and heat energy. Okay, so we'll discuss this very in detail along with zeroth law and first law of thermodynamics. Okay, this is a brief overview of today's class. And for tomorrow's class, we'll go to isothermal, adiabatic, all these processes. Okay, so is it clear to all of you? I'm a clear students. Shall we start? Go ahead. Please click on yes if you're ready. Okay. Awesome. Great. Good. Okay then. So then starting here very quickly. So here I've given a broad spectrum. Okay, so on the screen you can see a detailed overview of all the radiations available in universe. Okay, most of the radiation available in the universe are here. So we can start from radio waves. Radio waves are the waves which have highest wavelength. You can see radio waves can be as long as 1 kilometer. One wave of radio can be as long as 1 kilometer. So they have the highest wavelength, and as the wavelength reduces, we go towards microwave, infrared. Infrared is responsible for heating, if you know, right? And it is almost as small as a needle pinhead. Okay, needle point. It is as small as a needle point. And then if I go to visible light rays, visible light rays are very small. They have wavelength approximate like microorganisms. Okay, then after then comes ultraviolet X-ray. You all know the applications already. I studied that in 12th once, right? And the most smallest wavelength will be for gamma rays. Gamma rays are available in nuclear reactions, and they emit from sun and galactic outburst. Okay, when a star goes supernova, in that case gamma rays will be emitted. Okay, and these are different kinds of radiation. And what is radiation? Radiation is nothing but basically energy, right? When I say visible light, it means light energy. When I say infrared, it's almost like heat energy. Okay, so all the radiation carry energy. So when you stand outside, okay, facing the sun, your face or your body gets heat up because the radiation is going to heat you up. It's going to heat you up your body, right? So very simple. Radiation is nothing but pure energy. When that energy get transferred to you or any body, it heats up. Okay, that's as simple as that. Okay, so everybody heats up, and there is one object which heats very much. That object is called as black body. Okay, so what's a black body? So black body is an object which can absorb all the incident radiation on it. Okay, for example, if I go and stand near the sun, all the radiations I cannot absorb. Okay, some of the radiation will be reflected back, some of the radiation will be given out by the cloths. But if you keep a perfect black body, what happens is whatever the sunlight is falling, whatever the radiation is falling, everything will be completely absorbed. Good morning, Abhay. Good morning, everyone. So it's going to get completely absorbed. So black body is a very simple thing. Whatever radiation falls on black body, everything will be absorbed. As simple as that. So we can define something called as absorptive power or absorptivity. Absorptivity. What is absorptivity? Absorptivity is amount of radiation absorbed, amount of radiation absorbed divided by amount of radiation incident. Absorbed divided by amount of radiation incident. If you absorb all the radiation which is incident on you, then the ratio will become 1. Therefore, absorptivity of a black body will be equal to 1. Okay, black hole too, exactly. Black hole, whenever you cross the event horizon, all the radiation available will be absorbed by the black hole. So black hole also can be thought as a black body. That's correct. Good, Archana. So is it clear? So object with a absorptivity 1 are called as black bodies, which will absorb everything. Okay. So once it absorbs, it has to emit now. How much will it emit? Can you tell me, guys? Any idea? Any conceptual idea? So how much is it going to emit? Black body is going to absorb everything. How much is going to emit? What factors does it depend on? Could you guess or do? So an example of perfectly black body is sun is also perfectly black body because it absorbs all the radiation, it emits all the radiation. Okay, and if you take penta black, there's a paint called penta black. Even penta black absorbs all the radiation. That's also a black body. If you take a black hole is also a black body because it absorbs all the radiation. Okay, Smayak, cool, right? Okay. So now, okay, when absorption ka ho gaya, what about emission? So emission depends on the temperature. Depends on temperature. If the object is very hot, it's going to emit a lot of radiation. If the object is very cool, it's going to emit low radiation. For example, our sun. Our sun is very hot, so it's going to emit most of the radiation. Okay, but if I paint my home completely black, it's not going to emit all the radiation. It's going to keep some radiation as it is, right? So emission completely depends on temperature. So you should remember that. And also emissive power E, or also written as P, is equal to heat energy divided by unit time divided by unit area. This is one of the most important formula you're going to use in numericals. Okay, the emissive power of a body is equal to amount of heat energy emitted per unit time per unit area. Okay, so amount of heat energy, this is heat energy, okay, by unit time and unit area. Unit time and unit area. So I believe you are clear with what is absorptivity and emissivity, right? So how much if I put 100 becquerel of radiation, if it absorbs 98% of radiation, absorptivity is 0.98. Okay, and how much the radiation is going to emit is it depends on the temperature. So let me tell you how does it depend. Okay, give me a second here. Okay, so I'm going to show you a small simulation. So can you guys see the screen here, what I've shared? Okay, so I'm sharing you here a small simulation. Okay, so in this small simulation, can we call this intensity? It is proportional to intensity. Okay, Archana, it's not exactly intensity, but it's proportional to intensity. Okay, that's correct, Mega. So here, students, here is a small simulation. Okay, what I have plotted here is spectral power, the power or intensity I have plotted in the y-axis, and in x-axis I have plotted, wavelength of the light. Okay, now I'm setting the temperature to 200 Kelvin. Okay, Earth's surface is almost 200 Kelvin at the poles. It's very cold. So Earth doesn't emit light. So you can't see any graph here. There is no curve. Okay, but as I increase the temperature a little bit, okay, now notice I'm increasing the temperature to 700 Kelvin. I slowly increase to light bulb. When you come to the temperature of a light bulb, 3050 Kelvin, you can see there is some amount of light getting emitted. Okay, and where is the most amount of light? Most amount of light is in infrared region, right? Most amount of light bulb. See, light bulb is going to emit all the different wavelength radiation. It is emitting yellow color, green color, red color. It's going to emit all the different colors, but mostly it is Now you can see the color here. In this color, you can see the light bulb color, and the most highest emission wave is here. And now let me increase a little bit from light bulb to sun. Okay, I'm increasing the temperature not a little bit, very high. Yeah, see. As I increase the temperature, you can see that now the emission intensity has gone up. It's emitting a lot of light. Okay, the area is proportional to the energy. It is emitting a lot of energy of this curve. And notice now the highest peak is in visible region. It has become completely red now. The object is completely red. Now let me increase the temperature a little more to 5000 Kelvin. Okay, so we are close to sun. Now in this 5000 Kelvin temperature, you can see highest peak emission of an object. It's going to emit blue color light, it's going to emit green color light, it's going to emit yellow color light, but most of the light is yellow color. Okay, and now let's check what will happen to our sun. Okay, yeah, see, so this is our sun. So when I go to our sun, you can see that our sun is going to emit lot of ultraviolet rays because it peaks at, good morning Jagan, at 6000 kelvins. You can see this is the temperature of curve of our sun. It is emitting infrared also, it is emitting visible light rays, it is emitting ultraviolet light rays, and some gamma rays also will be getting emitted. But you can see most of the light is coming from sun are violet. It's between visible and violet, ultraviolet light rays are being emitted. And if you do that, if you keep on increasing, see, this is how you get the curve. And at highest temperature, the object will look blue. You can see this is how the object looks like. Okay, see that dot here, this part, BGRK pass big dot, see there. Now the object is red. I'm heating the object. As I heat the object, color changes to yellow. Then it changes to light yellow. Then it is changing near to blue, almost white. It becomes almost bluish white at highest temperature. Am I clear to all of you? So this is how we do the experiment and find out what are different wavelengths are getting emitted from a hot object. Okay, coming back to the slide here. So let me tell you what's happening very quickly. So I'm going to plot wavelength in x-axis. I'm going to plot intensity or power in y-axis. Okay, at low temperature, I'm getting most of the infrared low wavelength light. Okay, I'm getting IRAs. Now I'm going to increase the temperature. When I increase the temperature, the light rays will be much stronger. Instead of infrared, I'm going to get visible now. I'm going to get more visible light rays. Now if I increase the temperature a little bit more, okay, little bit more, instead of I'm getting visible here initially. Now if I increase from visible to higher temperature, I'm going to get ultraviolet light rays. If I increase more temperature, like a supernova, then I'll be getting more of a gamma rays. So yeah, so what's happening here is, as I increase the temperature, wavelength is reducing. Can you notice that? Okay, at 3000 Kelvin, I'm getting around 1 wavelength. At 4000 Kelvin, I'm getting 0.6 wavelength, something like that. See, whenever you increase the temperature, wavelength is reducing. Is the idea clear? As you increase the temperature, the object is going to emit higher energy. Higher energy means low wavelength. Okay, and this law is called as Wein's displacement law. Lambda is T is proportional to 1 by lambda, or lambda T can be written as constant. It can be written as constant, or lambda1 T1 of one situation will be equal to lambda2 T2 of second situation. And this is called Wein's displacement law. Why it is called as displacement law is because as I increase the temperature, the peak is going to shift, right? The peak is going to shift from one point to other point. You can notice the shift in peak. Okay, and lambda1, what is lambda1? Lambda1 is the peak wavelength. The topmost wavelength is called lambda1. Okay, and this next topmost is called as lambda2, and the next topmost is called as lambda3. So this is called as Wein's displacement law. Am I clear to all of you students? Respond in chat box. Click on yes or no if you have understood. Okay, clear, right? Okay, good. Okay, so okay, Abhay, cool. Okay, lambda1 is equal to lambda2. Lambda is the wavelength, T is the temperature for different situations. Okay, and then we have one very simple law. Okay, one simple law is called a Stephen's law. Imagine I have a black body, and this black body has temperature T. And whenever black body has a particular temperature, it is going to emit radiation. I told you, right? How much radiation it's going to emit depends on temperature. Therefore, the emissive power for black body can also be written as T to the power of 4. It is proportional to temperature to the power of 4. It also depends on emissivity, how much emissivity it has. Okay. Black body will emit all the radiation, but if you take regular bodies, they won't emit all the radiation. So emissivity is a constant number. It depends on emissivity, and also depends on sigma. Sigma is called as Stephen's constant. Okay, and don't worry, Stephen's constant will be given in exam whenever the problem is given. So this is called the emissive power. Emissive power. Okay, and emissive power is also equal to this one. I told you, right? Emissive power is equal to heat energy divided by time divided by area. So yeah, there are two formulas for emissive power. This is with respect to heat energy. This is with respect to temperature. Okay, where T is called the temperature of the body. Okay, E is called the emissivity of that particular body. Emissivity. Okay, and sigma is called as Stephen's constant. Stephen's Boltzmann constant also. Sometimes they call it Stephen's constant. Cool. So this is a very simple law. That means the higher you increase the temperature, the more higher the power which is going to get emitted. This is in vacuum. This is in vacuum. But what if you have a black body of temperature T surrounded by an atmosphere of temperature T naught? In that case, power emitted will be equal to sigma emissivity T to the power of 4 minus T to the power of T naught to the power of 4. That means if there is atmosphere also, when there is atmosphere, the emissive power becomes very less. Thoda less hoga because gradient come hoga na temperature ka. Let's say it becomes a bit less. Is these two laws are clear? So whatever questions you get in mains, advanced, or JEE from this concept, it will be almost direct. If you know the formula and if you can understand the question, you can answer it very quickly. What is the name of PB? Power of black body. Okay, PB is power of a body. Okay, power of a body. How much power is getting emitted by the body is called as PB. Okay. Is it clear, students? Very simple. So whenever a black body absorbs everything, absorptivity, emissivity now, and whenever you heat the temperature, the color of the object changes, and because of that, we can define Boltzmann's, Wein's displacement law. Then we have studied Stephen's law. Now let us solve some problems on it. Okay, just theory is not enough, right? Now let me tell you one simple question here. A black body radiates power P. Okay. And maximum energy radiated around by it is of wavelength lambda. So the black body is emitting power P, which has wavelength lambda. Okay, highest wavelength of the black body is lambda. The temperature of the body is now changed. So this is case 1. Okay, now there is case 2. Now they're increasing the temperature of the body. Okay, when they increase the temperature of body, it is going to emit now 3 lambda naught by 4. At initially T naught temperature, it was emitting lambda. Now at a T dash temperature, at a different temperature, it is emitting 3 naught lambda by 4. Okay. Now, what is the power radiated by it? Initially, if the power is P, now what is the power radiated by it is a question. Okay, a very simple question. Did you get the question? So at initially a temperature T naught, the object was emitting lambda naught and the power coming out was P. Now the temperature is increased to T dash. Now what the wavelength you're getting is 3 lambda by 2. Now what is the power they're asking? So now as I told you students, power you can calculate by using temperature or by using energy. So here I can find temperature because in question also they have mentioned temperature, right? So we'll try to consider temperature. If T naught, initial temperature is T naught and wavelength is lambda naught, final wavelength is 3 lambda naught by 4. Can you tell me what is the final temperature? What is T dash? By using this law, our Wein's displacement law, using Wein's displacement law, can you tell me what is the final temperature? Please check, try it out. Exactly, right? Good. That's good answer. Come on, guys, all of you try. Yes, Archana. Yes, Shishir. Good. Okay, keep trying, all of you. Very simple, right? So according to Wein's displacement law, I can write lambda 1 T1 initially will be equal to lambda T2 finally. Initial is wavelength lambda. Initial temperature is T naught. And final wavelength is given as 3 lambda naught by 4. And final temperature is T dash. Lambda will cancel out. 4 will go to numerator. 4 by 3 T naught is equal to new temperature. So here this T dash can be written as 4 T naught by 3. Okay, 4 T naught by 3. This is a new temperature. This is the new temperature what I'm getting. Abhi to temperature mil gaya, power bhi mil jata hai aaram se, right? So what I have to do is power is equal to sigma E T to the power of 4, right? Or P dash will be equal to T dash to the power of 4. I have to write new temperature. Okay, so what is the new temperature? Let me write sigma as it is, E as it is. New temperature is 4 by 3 T naught to the power of 4. That is the new temperature. Therefore, P dash will be equal to sigma E. 4 cube is 256, 3 cube is 81 T naught to the power of 4. This whole thing can be written as P naught, because in this is T naught matlab initial power. So I can write this as 256 by 81 into P. So my answer is that option A. Am I clear? Am I clear to all of you? So click on yes if I'm clear. If you need any clarification, please let me know. So very simple. Power can be found out by using temperature or energy. And if wavelength is given, use Wave's displacement law and find temperature. From temperature, use Stephen's law to find out power. Okay, this is Wave's displacement law. This is Stephen's law. Clear to all of you? Click on yes or no, students, if it is clear to all of you. Okay, and YouTube guys, you can respond me in the chat box. Okay. You want me to repeat? No, right? Okay. Cool. Okay, guys. Okay, great. Very similar question, but I want you to try for this. Okay, want you to try for this. Now, two bodies A and B have thermal emissivity. So there are right two bodies. Okay, first. So there is body 1 and there is body 2. This body has emittivity 0.01 and this body has emittivity 0.81. The outer surfaces are equal of two bodies. The area is same. Two bodies, and next point is the two bodies emit total radiant energy at the same rate. That means whatever they are radiating energy, it is at the same rate. Therefore, power of 1 is equal to power of 2. It's given clearly. It is energy is emitted at the same rate. The wavelength lambda B correspond to maximum spectral of B. So they're calling it, this is object A and object B. This is giving lambda B as a maximum wavelength. Okay, and now we can understand that the wavelength lambda B corresponds to maximum spectral radiancy from B, and it is shifted from the wavelength corresponding to a radiancy by A by a factor of 1 micrometer, and there is lambda A, and they differ by a factor of 0.1 micrometer. Okay, as simple as that. Now they are given temperature of A is equal to 5529 degrees Celsius. So temperature also is given for this. Temperature is also given for this. Now, my simple question is, can we find temperature of B? Okay, can you try this out, guys? So power of 1 is equal to power of 2. Temperature of A is given. Temperature of B is unknown. Okay, and lambda 1 and lambda A differ by a factor of 1 micrometer. Lambda A minus lambda B, they differ by a factor of 1 micrometer. Okay, now I can't use Stephen's law because lambda 1 T1 is equal to lambda 2 T2. I know only temperature T1. I know the differences of lambda 1 lambda 2, but I don't know their value. So I can't use the Stephen's law. Therefore, use this trick here. What they have given, P1 and P2 are same. Okay, so we know that what is P1? P1 is equal to sigma 1 E1 T to the power of 1/4 according to our Stephen's law. Then sigma 2 E to the power of 2 T to the power of 4 according to Stephen's law. Am I correct? Stephen's constant will be always same. Whatever situation you take, it's a constant number. They cancel out. Now we can find out. Emissivity is given for both the objects. So please try to find out, guys. Now, okay. What do you think? So emissivity is given for 1, emissivity is given for 2, temperature 1 is given, temperature 2 is given. Why I want you to try is, this question is very simple, but you need tricks to solve it, or not tricks, but you should be very good at mathematics to solve this. Okay. So try it out along with me. So emissivity is given as, students, 0.01 for object 1. Okay. Temperature 1 is how much? It should be always in Kelvin. Okay, not in Celsius. Okay, 273. So it becomes 5802 to the power of 4 is equal to emissivity of second object is 0.81 and T to the power of 2 to the power, temperature second to the power of 4. Now, can you do you think you can take the fourth power of 5802. It becomes a very, very large number. So you can't do this. So best way to do this is simplify and take the fourth root first. Okay. So keep this 0.01 here itself. Bring 0.89 to the 81 to the denominator. 5802 to the power of 4 stays there, is equal to t to the power of 4. Next, best way is take the fourth root here, take the fourth root of the whole equation. Okay, that's the best way to go ahead. Okay, and this is cancel one decimal point, cancel one decimal point, cancel both decimal point, it becomes 81. It is equal to 1 by 81. 1 by 81, fourth root is 1 by 3. Okay, and 5802 to the power of fourth and fourth root stays cancel out and become just 5804, and fourth root will cancel out, becomes t2. Therefore this is almost equal to, this is on, let me divide 5804 divided by 3. So 1934 Kelvin is the temperature of 2. So this is how you find T2. Okay. Am I clear, students? So either you can use Stephen's law to find or Boltzmann law. Just choose whichever is comfortable and whichever is easy. Am I clear to all of you? And I'll leave you to solve what is lambda b. Okay, once you know temperature 1, temperature 2, and they are also given the lambda a minus lambda b difference, you can find out lambda b. So I'll leave the second part for you to solve. Okay. Is it clear, students? Is it clear about these two laws? These two laws are very simple. Okay, but they differ in application level. I'll share you the model. Please go through the questions also to solve much more questions. Cool. So the second part will be left for you to work it out. Okay. Cool, right? Any doubts, guys? Any doubts from thermal properties? So in thermal properties, we have discussed length expansion, volume expansion, heat transfer, Newton's law of cooling, radiation. If that's completely clear to all of you, we'll move ahead to thermodynamics. Okay. Are we good to go? So 30 minutes is done. So the rest of it we'll dedicate for thermodynamics. Click on yes, students, if you are clear and if you are ready for this next section. Clear, Abba? Okay, good. Okay, Aditya. Yes, okay, Anusha, cool. So now, okay, Abhay, okay, Abhijit, thank you. So now switching from thermal properties to thermodynamics. In thermal properties, we're discussing about objects. What is the expansion of metal? What is the expansion of plate? How does heat transfer from one object to other object? Rate of a black body. But in thermodynamics, we usually discuss about the same things, but only for gases and ideal gas and real gases. So we usually do thermodynamics for gases. We can also do it for fluids, but it's not efficient. So we'll try to do it for gases. Okay. And as the name itself tells you, thermodynamics. So dynamics of temperature, dynamics of heat. So in gases, how does the heat flow? Is a purpose of thermodynamics. So if you know how the heat flows in gases, that's all is there to learn about from this whole chapter. Okay, so remember in thermodynamics we'll be talking about gases and how does heat move from one point to other point of the gases. And to understand thermodynamics, we should have few basic understanding of parameters called pressure. Okay, pressure. Next volume. Next temperature. Next is temperature. And lastly, we should know what is number of moles. Okay, number of moles. Yeah. So you know what is pressure, right? So pressure is nothing but if I take a balloon now, okay, if I take a balloon, okay, and if I blow the air to the balloon, it completely fills the air from our lungs will completely fill it, and the balloon expands because whatever air molecules we have sent into the balloon is going to collide always with the surface of the balloon. They keep colliding everywhere. They keep colliding them among themselves, and they keep colliding with the wall. So these molecules are going to exert force on the boundary of balloon, that is called as pressure. Unit will be pascals. Okay, and volume, as you blow more air, the balloon becomes more bigger and bigger, and it's going to occupy more space. And usually meter cube is the SI unit, and this is nothing but how much space it is going to occupy. And temperature, so it depends. Is the air water blowing cold, but since we are blowing it from our mouth, it will have the body temperature. So temperature parameters also is very, very important to understand the thermodynamics. And number of moles, what's the quantity of gas? We can't tell kg or liter for gas. We usually call it in moles. In very, very small scale, we'll call moles as quantity of gas. So I'll not discuss this much on these 4 parameters because they're very simple, and I'm pretty sure all of you know about it because you're studying it from 2 years. But the things which we need to understand very clearly are what is work done, what is heat supplied, and what is internal energy, what is entropy. So these are the 4 parameters which we need to understand very clearly. And as the agenda for this chapter, we have to concentrate on finding these parameters for 4 thermodynamical processes. Okay, how to find heat, how to find work done for 4 thermodynamical processes like isothermal, adiabatic, isochoric, and isobaric. As well as there is high probability of you getting a question from graphs, TV diagram, or TP diagram, or PT diagram. One question you getting from this chapter is where this topic is very highly probable. Okay, they might give you a graph and ask to find this 4 parameter, or they might give you a numerical and ask you to find this 4 parameters. Something like that will happen. Or next will be like heat engine efficiency, refrigerator. That will be one more part for this. Okay, cool. So now let us jump ahead. I'll tell you very in detail how to find work done, when it is positive, when it is negative, when is heat positive, when is heat negative, what is internal energy, and what is entropy in today's section. Entropy I'll try to cover in today's section, okay, as much as possible. Okay. So guys, and always remember, whenever we're discussing about this chapter, we'll be taking piston. Piston is our laboratory now. Okay. So what's a piston? There will be a cylinder, a very solid cylinder, and the solid cylinder will be filled by gas. And I'm going to cover it by piston. You can see the left diagram. Okay, piston is like a cap, but this cap can move up and down. If I pull the cap, it comes up. If I push the cap, it goes down. So this arrangement is called a cylinder piston. Okay. Am I clear? So now I'm taking a regular cylinder, and there is a piston now. There is a piston too. So nothing to worry about it. And the thing is, this empty space is filled by gas now. So there will be pressure for this gas, there will be volume for this gas, there will be temperature for this gas, and quantity will be given by N of the gas. So simple. There are very basic terms. Now what I'm going to do now, I'm going to heat this gas, and I'm going to provide heat. So can you tell me what will happen when I provide heat? Any guesses? This piston is movable, okay, and it can expand or it can contract. It's completely free. If I provide heat to this cylinder, can you guess what will happen to the piston? Any idea, students? Just text me in the chat box. What do you think it's going to happen when I heat this piston? When I heat the piston, the heat will transfer from the cylinder to the gas. Okay, that's correct, Deepak. Good. Okay, moves up. Good, guys. Good, goes up. So because of increase in temperature, the kinetic energy of molecule increases. When the kinetic energy of the molecule increases, they push up the piston. Now the piston is going to change its position. Okay, it is going to shift up by a little distance. Okay, by dx amount of distance, it is going up. And now when I provide heat, this goes up because there is a force being exerted. The molecules will exert some force on the piston, and due to that force, the piston will go up by distance x. So now I can find out what is work done very easily, right? So what is work done? We know that work done is equal to force into dx. We know this. dw is equal to f into dx. We have studied this from almost 2 years, right? Now, but for gases, I don't want force. The best way to express is multiply this term by A and divide this term by A. So there is no change in the total formula. Force by area will be called as pressure. Area into distance will be called as volume. So therefore, dV, work done, whatever I provide heat is converted into work, and that work is nothing but P dot dV. P dot dV. Okay, very simple and very important. Good, guys. Good. The piston goes up when I heat it, and when I extract the heat, the piston will come down, and that amount of work done is equal to PdV. It depends on change in volume. If volume changes, there'll be work done. Okay, and this can be done in two ways, but in a very simple manner. Okay, just a minute. Yeah, which is, one is the integral form, other is the algebraic form. How does the integral form looks like? So work done is equal to integral of P dot dV. Okay, and work done is equal to P into V2 minus V1. This is algebraic. Okay, so either if there's only two state, initial and final, you can use P V2 minus V1, because dV, change in pressure volume, is V2 minus V1. But if there are many steps, 100, 200, 300 steps, then you can use the integration. Okay, that will be easiest way to calculate work done. Okay. And okay, so now the sign convention, when is work done positive and when is work done negative? So this is very, very important, right? So imagine there's a car. If there's a car, you want the car to move. I mean, do you want to push the car? No, the car wants to carry you. So whenever the system does the work, okay, whenever system does the work, whenever a system gives the work, it is called as positive work done. When the system do the work by itself, for example, refrigeration cools the ice, it is doing by itself, right? So work done is positive. The car is going to move and car is doing the work, so work done by car is positive, something like that. Whenever the system gives the work outside, it is called as positive work. Or imagine now the car is or the cycle is punctured or the car is punctured. Now you have to push the car. When you have to push the car, work done will be negative. Okay. So again, like generally, we also don't want us to do the work. We want the objects to do the work around us. When the objects do work around us, work done will be positive. When we do the work done will be negative. Okay. Cool, right? Okay, so let me summarize here. No problem, bro. Okay, so now students, I told you that work done dW is equal to force into displacement. This is just what you're studying from many days and many years. I'll divide by area and I'll multiply by area. Force by area we have studied in last chapter. It is called as pressure. Dx into area will be called as volume. So you get dW is equal to PdV, and two different ways of writing this formula are very simple, which is one, P into V2 minus V1, because dV means change in volume. Otherwise, integral of PdV. Integral of PdV if it is a continuous smooth process. So these are the two ways to find work done. And if I take a system, if the system gives out the work, it is positive. Okay. If I do the work, it is negative. It is very easy to remember, right? Am I clear to all of you? Is it clear, Abhay? Okay. Sir, why you divide and multiply by? Bro, simply like force is not a good term to understand gases, but pressure is an easy term to understand gases. For gases, you can't measure distance they travel, but you can measure the volume. So for gases, we usually can measure pressure and volume easily than these two. That is why I converted in this formula. Okay. Clear to all of you students? Is the sign convention clear? It's very easy to remember. जब system work करेगा, work positive होगा. Okay. Yes. Okay. Anisha. Okay. Thank you all of you. So next, work done का हो गया. So now we know the formula. When is work done positive? When is work done negative? Depending on the situation, depending on the problem also, we can find out whether they're negative or positive. I'll show it very soon. Next important thing we're going to talk about is heat, dq. So if I want to expand this, piston, if I want to move this piston, I'm providing some heat. Now I need to heat the gas. So whenever you provide the gas, it is positive. Okay, now take the same system. Whenever you provide the heat, it is positive, and whenever you take the heat, it is negative. Opposite to work done. Whenever you give the heat, and then it will be taken as heat is positive, and it's a convention, students. There is not much of a principle behind it. It's just the idea we followed. In chemistry, it is reverse, na? If you remember, work done is reverse in chemistry, and work done is reverse in physics. So don't worry, it's just convention. So if you provide heat to the system, it is taken as positive heat. If you extract the heat from the system, it is taken as negative heat. Okay, cool. And what is the formula to calculate dq? So dq is usually we already seen, right? It is equal to ms delta T or nc dt. For gases, we can use nc dt. I hope you remember, right? Yeah. Okay, we can use D is equal to nc dt. Okay, cool. So this dq formula is from last chapter. And lastly, we are going to discuss about a last parameter called internal energy, du. So du is called, this is work done, this is heat, this is internal energy. So what is internal energy? The total energy of the gas molecules. The gas molecules will be moving, the gas molecules will be colliding, the gas molecules have temperature, the gas molecules have kinetic energy, potential energy, molecular energy. So all of that energy together is called as internal energy. It's called as internal energy of the gas molecules. And it also has a very, very similar formula, just like Q is equal to nc dt. This also has a very similar formula. It is equal to nc dt. Okay, but usually what you need to understand is that if I increase the temperature, there is increase in heat, there is increase in internal energy. Okay, they're directly proportional. Okay, they're directly proportional. You will understand in next class. Sometimes I'll write CP here, sometimes I'll write CV here. Okay, don't worry, I'll tell you that in the next class, because abhi zarurat nahi hai. Okay, so now, but remember, whenever you increase the temperature, change in heat also increases, and change in internal energy also increases. When you decrease the temperature, heat also will decrease, internal energy also will decrease. So this is something which you can easily understand. Okay. Am I clear about these three parameters? How to find work done, how to find Q, how to find U? Please let me know in the chat box if it is clear, students. Okay, good. Yeah, so very simple, right? Work done is equal to PdV, and dQ is equal to NCdt. For du, we can use first law of thermodynamics. I'll tell you that. Okay. Yeah. Cool. So moving on to laws of thermodynamics. Now I'll just explain you zeroth law and first law. So what is zeroth law? If a block A is in equilibrium with B, if block B is in equilibrium with C, I mean thermal equilibrium, therefore A will be in equilibrium with C. I mean, this is very, very simple law. Okay. So if A has the same temperature of B, and if B has the same temperature of C, then A and C have the same temperature. That is something which we have understood, right? Okay. Cool. So that, don't worry about that. Not much of problem will come, but that's a basic principle you should understand. We already seen this yesterday in thermal equilibrium. So let me quickly come to the first law of thermodynamics. So what is first law of thermodynamics? So first law of thermodynamics tells us that whatever heat you provide to a system, that will be distributed as work done and as internal energy. So let me give an example. Now there's a coffee kettle and you're heating the coffee kettle. So when you heat the coffee kettle, what will happen? The temperature of the coffee will increase. Okay. And sometimes the coffee kettle will come up, like it will, because of increase in steam and pressure, the cap might come out. So what's happening? Here it's very simple. Temperature is increasing for the liquid and the cap is coming out. So work done is also happening. So whenever I provide heat, temperature zyada hoga and work done bhi hoga. So the same thing is written in numerical way. Whatever heat you provide, it is converted into increase in temperature or work is being done. Simple. Am I clear to all of you students? Yeah. Okay. So even you can use this formula. Any doubts, friends? You can ask me. Aishwarya, is it clear? So what I'm trying to say here is, let me repeat it again. Okay. So what happens here is, you have a coffee kettle, and when you have a coffee kettle, you're going to heat it. Very simple. So inside there is coffee or milk. Now what's happening when you do that? The temperature increases very slowly, right? And I told you very clearly that whenever temperature increases, heat energy increases, and whenever heat energy increases, internal energy also increases. Very simple, right? So here I'm heating the coffee, and due to increase in the heat of a coffee, internal energy will increase, and there's a chance that sometime the kettle also will come out. The kettle might also come out of the vessel. So whatever heat I provide to the vessel will be used as work done and will be used to increase the temperature. Am I clear now? Is it clear to all of you, YouTube guys? Yeah. Okay, good, clear, right? Awesome. So okay, then moving on to conservation of energy. This principle is exactly equal to conservation of energy. Whatever energy you're providing will be conserved. So for example, if you are in a room and if it's very, very cold and if you want to make the room warm, what you'll do? You'll put a heater, you'll take the heat from this point and you'll put it in the room. So this becomes more warm, but this room is going to become a bit cold. So it's conservation of energy. Whatever you do in this whole universe, energy has to be conserved. You can take from one system and put to other system. Okay, but you can't create it. You can convert chemical, you can burn the wood and increase the temperature. Here the chemical energy is getting converted into the heat energy. But the whole first law tells that the energy is conserved. Whatever you provide, it will be saved as work done or heat. Okay, so that's simple ideology. Okay, so let us discuss more about questions now. Theory ho gaya. We'll come to questions, but last concept, PV graphs. PV graph. So why do we use PV graph? Imagine I have a balloon now. Okay, imagine I have a balloon now. So balloon has some initial pressure V and some initial volume V1, P1 and V1 are the initial values. Now I'm going to take a needle and pierce the balloon. When I take the needle and pierce the balloon, what will happen? The volume will reduce, the pressure also will reduce. Okay, so I'm making a graph for that. Initially, I had pressure P1 and volume P1. Now, after I put the needle to the balloon, the gases is decreasing, the volume is decreasing, it comes slowly, volume decreases, pressure also decreasing. And finally, it will lose all the gas and become to pressure P2 and volume V2. So this is something of what you get there. Okay, cool. Am I clear, students? Just a minute. Yeah. So PV diagram is very important, because if you know PV diagram, you can find out work, you can find out Q, and you can find out U also. How can you do that? So simply to tell you, it's very simple. If you have pressure in y-axis and if you have volume in x-axis, what happens? You are going to have, imagine you move from point 1 to point 2 in this way. And if you find out this area, what will happen if you find out this area? Let me take a simple example. So there is this process happening from point 1 to point 2. And if I calculate the area, what will be the area? The y-axis is given by pressure, the x-axis is given by volume. So area is equal to pressure into volume. Pressure into volume is nothing but work done. So always remember this concept, that PV graphs are there, and always the area of PV graph is equal to work done. So this is how you find it graphically, and this is the most important concept of today's class. Okay, this has a very high chance of appearing in question. Okay, cool. So please, make sure you understand this. Area of PV graphs is always equal to work done, because area of PV graph is nothing but pressure into volume, x-axis y dx, right? Y-axis into x-axis, pressure into volume. So what is in y-axis? Pressure. What is in x-axis? Volume, PdV. Okay, and you can also find out whether it is positive or negative. Always remember, work done is written as P into V2 minus V1 also. If the final volume is greater, if V2 is greater than V1, work done is positive. Okay, if V1 is greater than V2, that means if V2 is smaller, final volume to come ho gaya, then it becomes work done is negative. Work done is negative, because imagine in case number 1, pressure into 100 minus 50, you get 50 P. So this is positive work done. Imagine the reverse of it. Final volume is 50, initial volume is 100. So then it becomes minus 50 P. So in expansion, the work done is taken as positive. In compression, work done is taken as negative. Okay. So in expansion, if the object expands, the balloon expands, okay, or if the piston goes up, the volume of the gas increases, work done is positive. If the piston comes down, if the volume of the piston decreases, then it's taken as negative. Work done is negative. Clear to all of you? Students, am I clear to all of you? If we are clear, we have a good amount of questions to solve now. Okay. Cool, right? Okay, great. So now let me solve a very simple question, but very important question. Okay, this is very basic. If you can understand this question, both answer the rest of the problems. Now, this is a matrix match question, and now for the process JK. So what's happening here is, a process starts from J, moves to K, then moves to L, moves to M, and moves to J. Okay, a process is starting from J, going to K, then going to L, then going to M. So this is a simple process. Okay, don't worry. And there are different steps. J to K is one process, K to L is one process, L to M is one process, and M to J is one process. There are totally 4 processes here. Okay, and our first question is, in the process J to K, is Q is greater than 0, matlab is Q positive, is work done negative, or is work done positive, or Q negative. So that they want us to find out this information. From J to K, choose any one option. There can be many options, like Q and W can be there, but choose any suitable option. Okay. So process J and K, this is a process. Can you tell me, guys, what is happening here in this process? What is the work done for this process, students? What is the work done for JK? What is the work done? Yeah, very good. Exactly, right? Awesome. There is no change in volume. Simple. That's a very good understanding. Okay, so let me come back here. You can notice that pressure is decreasing from 30 to 10, but volume is same, right? So therefore, in the process JK, change in volume dV is equal to 0. Therefore, work done PdV is equal to 0. Okay, so therefore I can't choose any of this option. It is not 0 and it is not great. It's not positive, it's not negative, it's equal to 0. So you leave it. Okay, Abhay, work done is negative, not negative, bro. It is 0. Okay, there is no work done happening at all because the volume is constant. The volume constant होगा, PdV 0 हो जाएगा. Good guess for the answer. Okay, so yes, so the Q and R is not right. Now we'll check about heat. Here, pressure, what's happening to pressure? You can see the arrow mark of the process, pressure is decreasing. Okay, and from our ideal gas equation, PV is equal to nRT. Okay, whenever pressure decreases, temperature also decreases. Direct, right? So whenever pressure decreases, temperature also decreases. If temperature decrease hoga, what will happen to heat? Heat will also decrease. Okay, when heat decreases, it is negative. So then I can map process JK में heat decrease होगा. That means delta Q is negative. Okay, so A is equal to S. A is equal to S. Am I clear? Am I clear with the first process, student? Work done is equal to 0 because there is no change in volume, and Q is negative because pressure decreases and temperature decreases, and due to decrease in temperature, there's a decrease in heat. Cool, right? Yeah, awesome. If it is clear, then I want you to answer for KL. So now we are going to consider this process KL. What is going to happen to the work? What is going to happen to the work? Exactly, Aditya. So now you can see that initial volume was 10, the final volume is 20. Okay, final volume is 20. So positive, work done is being positive. So that therefore I can put KL is equal to अच्छा work done तो ज़्यादा हो रहा है. It's not negative, sorry. It's positive. Work done is positive. Okay, because increase in volume, as I told you, expansion में work done always positive होगा हमेशा. So therefore B is equal to R. Okay, and also you can do it for Q. Whenever volume increases, work is done. I agree, but volume increase तो temperature भी बढ़ जाएगा. Temperature also will increase, and whenever temperature increases, Q also increases. So this will have a multiple option. KL will be equal to increase in temperature also. You can map it to increase in temperature. Okay, so let me choose a different color, okay, to avoid confusion. So KL have positive heat and positive work. Okay, why positive work? Volume increases. Why positive heat? Because when volume increases, temperature increases, heat increases. Am I clear? Why this has two options? Am I clear to all of you? Students, is it clear? Right? Okay. Good. So moving on to next question then. So let me know what will happen to process LK. If I don't go from K to L, but I'm coming back from L to K. Can you tell me what will happen in this case? I'm coming from L to K now in opposite direction. That's correct. So there is a decrease in volume. जब decrease in volume होगा, what will happen? Work done will be negative. Okay. Yes. Good, Prakash. So work done is negative for uh, L to K, and volume also decreases, and due to decrease in volume, temperature also decreases. Therefore, heat also decreases. Okay. As simple as that. So this is how you map, and this is how you need to understand. There'll be many such questions you'll be getting, and you should try to understand. Okay. Now I want all of you to give me what are the correct options for MJ. I'll not do anything. Just sit quiet. Tell me what are the correct options for MJ for this process here. If I go from M to J, what will happen to work and what will happen to heat? Just tell me about work. What will happen to work? Work done is negative, right? Because volume is decreasing. It's coming from 20 to 10. So compression हो रहा है, इसलिए volume becomes negative. But you can't give direct information about heat. Okay, you have to do problem only, because you can see in that diagram, okay, pressure is increasing by +10 and volume is decreasing by -10. So you can't actually tell what happens to Q unless you solve the problem. So just in that case, just point it to negative work. Point it to negative work. Okay, cool. Sort ho gaya. Nothing to worry. Okay. Yes. So yes, I mean, this is why I solved this problem, is just to give a clear idea. If you are given the graph, how to tell whether heat is increasing or work is being done or work is not being done. So just to get that idea, I just told you that. Now we can jump into regular questions. Okay, that was a very conceptual based question. Now let's jump into regular questions. So in this question, what's happening? Okay, when water is boiled at 2 atmosphere, so there is water and it is boiled at 2 atmospheric pressure, the latent heat of vaporization, okay, is 2.6 into 10 to the power of 6 joule per kg. Okay, and boiling point is 120 degrees Celsius, and at this pressure mass of the water is 1 kg. Okay, initially volume was 10 to the power of -3, and it is now converted into 1 kg of steam, and it has a volume of 0.801. Okay, now can you compute the work done in converting 1 kg of steam, converting water to 1 kg of steam? If I want to convert steam to water, water to steam, how much work should I do? So here they have given pressure, they have given latent of vaporization, they have given boiling point, they have given mass, V1, V2, all are given. So you just need to tell me again. So explain M2J. Acha. So bro, what happened in M2J was, so here was a graph, right? The graph was going like this. You can see that volume is decreasing. It was coming from 20 to 10 meter cube. So decrease in volume, matlab work done is negative. Compression, na work done negative ho jayega aaram se. But how can you comment on heat? No, you can't actually comment on heat, because here volume is decreasing and pressure is increasing. So PV is equal to nRT, right? यहाँ pressure बढ़ रहा है, volume कम हो रहा है, but they balance out each other exactly. If they balance out, then there is no change in temperature. So to be more accurate, you have to solve the numerical to understand it. Otherwise, we are good to go. Okay. Cool, right? So guys, can you tell me how much is the work done? Just it's a very simple question. Try to analyze how to find out work done. It's a simple formula. Give me the answer in the chat box, students. So work done, we already studied as integral of PdV, or there are only two process. It is equal to V2 minus V1. Pressure is equal to volume. So work done is equal to pressure into V2 minus V1. Okay. So what happens is work done is equal to, what's the pressure here, guys? It is given as 2 atmosphere. 2 atmosphere, matlab 2 atmosphere is 10 raised to 5 Pascal. It's given the question itself. I have written the pressure into volume. Initial volume is final volume is 0.801 and final volume is minus 10 to the power of 3. Minus 10 to the power of 3 means how much? Okay, it will be very small, right? It will be 0.001 minus 0.3. This is the initial volume. Therefore, work done is equal to 2 into 10 to the power of 5 into 0.8 into 0.8, and therefore work done is equal to 1.6 into 10 to the power of 5, or work done is equal to 1600 kilojoules. So this much amount of work should be done to convert steam and water into steam. Am I clear? Am I clear to all of you? So see, initial volume is given now, final volume is given now, pressure is also given. So just find it out. Ho jayega aaram se. Okay, nothing to worry, nothing to bother much. Okay, so as simple as that. Okay. So my next question is, if this is clear, student, I'll go to next question. Same here itself. Point 2. what is the amount of heat given? So we found out work done. Work done is equal to how much? 160 kilojoules was given. What amount of heat? What amount of heat is given to convert water into steam? To convert water into steam, how much heat is given? Work done to mil gaya. Yes. So now Aditya, I'm using the latent heat now. Okay. So what amount of heat is given to the water to convert it into steam? So just think about it, how to solve this. So now we have water, but we want steam. Okay, what's happening here? There is change of phase. If you be more clear, water is getting converted into steam. That means there's change of phase. Whenever phase change hoga, I know that the Q for phase change is equal to mass into latent heat. Mass into latent heat. Therefore, Q keep as it is. What is mass of the water? It's given as 1 kg. And what is latent heat? Latent heat is given as 2.26 into 10 to the power of 6 joule per kg. So all of them are in kgs and joules. So kg cancel ho jayega. The amount of heat I need to provide is 2.26 into 10 to the power of 6 joules. So this is the amount of heat that I need to provide to convert water into steam at this particular temperature. Am I clear? So this is how it happens. So don't forget. Whenever phase change happens, so try to remember the concepts from the past class so that you won't forget. Okay. Am I clear to all of you students? Any doubts? Please let me know if I have any doubts. Okay. Good. All clear, right? Why did I use ML and how did I find work done? So this is pretty simple. And let me ask you a very question and launch an MCQ for all of you. So here in this simple question, student, you can notice one thing happening. An ideal gas of mass m in state A goes to another state B via 3 different processes. So one is at the bottom, 2 processes in the middle, 3 processes happening at the top. If Q1, Q2, Q3 denote heat absorbed along 1, 2, 3. Now option A, Q3 is greater than Q2 and 1. And option D, Q1 is greater than Q2 and 3. And there are 2 other options. So what do you think will be the right answer for this? Take a minute, work it out. Have launched poll for Zoom students. YouTube students, you do try it out. Okay. So let me know the chat box. Which will be the right answer, do you think? Okay. So come on, guys, keep trying. So I need more answers to discuss the solution. If there is more participation, it will be better now. Good, Prakash. That's the correct answer. Okay. Yes, exactly. So I'll give you 30 more seconds, students. Then I'll solve the question. So until then, you have all the time to think it out. Okay. So Om Rawat, correct. Abai, could you check it again? Okay. So let me end the poll, guys, and let me discuss you the solution. Okay. It's more of a simple idea. So what's happening here is there are 3 processes, and you should be very careful about this concept. Okay, which is okay. This question needs to make you understand about internal energy. So all the 3 processes start from point A and end at B. Okay, when the initial and final points are exactly same, okay, that means initial temperature and final temperature will also be same. Jab temperature same hoga, change in internal energy will be 0. Always remember that. Always remember. Okay. Exactly. Yes, Aditya. That's what I'm trying to say now. So internal energy depends only on initial and final points. If temperature initial, okay, here, this point, and temperature B are same for all of them. Okay, for all the 3 processes. T1 is equal to T2 is equal to T3 for initially, and all the 3 points ended same. T1 final is equal to T2 final is equal to T3 final. When all of these 3 processes start and end at the same time, All of them have same internal energy. So change in internal energy is 0. So this depends only on points, not on path. It depends only on points. Okay, that's about internal energy. It's a point function. It's called state function. And work done it depends on area. As I told you, work done depends on area. It's called a state function. So work done will depend on area. Okay, it's called a path function. What if the path is different, then area is different. Okay, and therefore dq is also equal to path function. Okay, so if dw, if you have an equation like dq is equal to du plus dw, okay, du doesn't depend on path. If there, since dw depends on path, dq also depends on path. Okay, don't worry about this. I'm going to be more clear very soon. But now we'll come to the question here. This is process 1, this is process 2, this is process 3. All of them are having initial same points. So all of these three have same internal energy. So change in internal energy will be equal to 0. Therefore, the first law, dq is equal to du plus dw. For all the three equations, du is equal to 0. Therefore, dq is directly proportional to dw. It is directly proportional to dw. So you can very easily notice that for the first case, work done is this much. Work done is less. It has lesser area. But for second case, work done is little bit higher. And for third case, work done is much more higher. So you can easily, from the area of the graph, you know that area of 3 is greater than area of 2 and area of 2 is greater than area of 1. Therefore, work done in 3 is greater than 2, greater than 1, right? Because work done is directly proportional to area and it's also directly proportional to dq. So therefore, dq3 or q3 will be greater than q2, will be greater than q1. Am I clear to all of you? Okay, correct, Jagan. Abhay, could you check it again? Abhay, is it clear now? So this is how it happens. If you increase the area, Q increases since delta U is equal to 0. Since delta U is equal to 0. Okay. Okay, cool, right? Shall I move on to the next question then? Yes. So this is one simple question which will give you much more idea about many problems. Okay, so try to understand this question very clearly because it has all the parameters what you need to understand. Okay, for this concept, our system is taken from state I to state F. So initially a process will start from here, then the process will go to F. Okay, and along two paths. It can go along IAF or it can go along IBF. So there are two different paths. I call it as path A or path B. Okay, cool. And it can come from F to I in this particular way. It can come to F to I in this particular way. And along the path IAF, so they are given some information, let it write down. So along this path, the first red color path, they have given that. Let us note it down. Q along the path IAF, QIAF is equal to 50 calories. Is equal to 50 calories. And work done along the path IAF is equal to 20 calories. So it's given in the question very clearly. So nothing to worry, right? Next. And along the path IBF, Q is given as QIBF is equal to 36 calories. Okay. Calculate point number 1, WIBF. Okay. So this is the question. So how do you think you can approach students? What are the idea you can use? Any guesses? Any guesses? So you should notice one thing, that even if you go from along the path A or along the path B, it doesn't matter, because for path A, initial and final point are same. For path B also, initial and final point are same. If the initial and final point are same, U is exactly equal. That's correct, Aditya. So U is equal to, U is same for both of them. So you can write that du1 is equal to du2 because initial points are equal to final points. Okay. So and from our first law of thermodynamics, dq is equal to du plus dw, or dq minus du is equal to dw. So du, right? So du ka formula is this one. This is a formula for du. Substitute here. Therefore, dq1 or q1 minus w1 is equal to q2 minus w2. Am I getting, guys? Am I clear here, all of you? So since initial and final point are same for both the processes, internal energy same hoga. If internal energy is same, you can write Q1 minus W1 is equal to Q2 minus W2. What is Q1? 50 calories. Minus what is U? W1 20 calories is equal to what is Q2? 36 calories minus W final. I don't know what is WIBF, so keep W as it is. So 30 minus 20, 50 minus 20 is 30. 30 minus 6 is minus 6. Minus 6 into minus W is 6 calories. So when you solve and when you add and subtract, you're going to get 6 calories. Okay, as a simple answer for this question, they're going to get it as 6 calories. So let us write it down here. This is equal to 6 calories. This is equal to 6 calories. Work done. Okay, it's very clear now. So now let us come to the second part of the question. Now let us come to the second part of the question. If W is equal to 13 calories, if W is equal to 13 calories, so try to solve it along with me. Along the path Fi. So W of Fi is given. Okay, so write it down very clearly. So W of Fi is 13 calories. What is Q of Fi? Okay, what is Q of Fi? They're asking this particular idea. So how can I calculate this? It's very easy if I know the first law of thermodynamics. Q of Fi is equal to U of Fi is equal to plus W of Fi. So that means Q is equal to W plus U, right? So whenever you provide it, internal energy increase hoga and what then be hoga. How do I find QF now? So if I know what is UFI and if I know WFI is already given as minus 13, so QFI mil jayega aaram se. How do I find UFI? What's the change in internal energy between F and I? So for that you can use first law for the first process. Okay, see, from I to F, work done is given as how much? 50 is work done. From I to F, sorry, heat is given as 50 and work done is given as 20. So therefore U becomes Q minus W. How much is the Q? 50. How much is the work done? 20. So change in internal energy from I to F. If you go from I to F, 30 increase hoga, and if you come from F to I, 30 decrease hoga. So therefore UF is minus 30 and WF is minus 13. So total heat becomes minus 43 calories. Minus 43 calories. So let me be much more very clear here. I'm going to tell you once again. Okay, so pay close attention. So in the process along A, it's given that Q is equal to 50, W is equal to 20. Therefore, if I use this first law for the I and F through A, I'll find out that U is equal to 30. It is positive 30 whenever it increases the temperature. So if I go in this direction, positive 30 hoga, but here pressure is decreasing, volume is decreasing. When pressure decreases, volume decreases, temperature also decreases. So 30 also decreases. So it will be minus 30 if you come from F to Y. Okay. Clear, right? Is it clear to all of you students? That is how you find the answer will be minus 43 calories. Minus 43 calories. Okay, so this is the time's up, students. I'll let you work it out for 3 and 4. Please try it out by yourself. If you have any doubts, please reach out to WhatsApp. Okay, so I believe you are present in Telegram or WhatsApp group. If you have any doubts, please reach out to that particular doubt. Okay, cool, right? So is the questions clear, student? Take care. Okay, stay home, stay safe, and if you are unable to solve question number 3 and 4, please let me reach out to ER, regular WhatsApp groups and Telegram. Okay, bye. Thank you, Nisha. Bye. Okay, YouTube guys, is it clear to all of you? Any doubts? No, right? Cool, guys. Cool. So then let me end the stream. Okay, bye. Take care.